it's much easier to get a tutor in Math 30 or 130 or 180 than those.
So like where do you usually hang out within the school?
Oh, within the school, that's good. Where you usually hang out? Well, Goat Hill Tavern, actually. Well, usually here in Lewis, you know, in the division, you know where the dinosaur is? That open.
Okay.
That's the division office in there. I'm usually at one of those computers. Yeah. Okay. But again, if we can still make a specific time if you have.
Yeah. Okay.
Yeah. So you don't have to guess. So. Okay. All right. Any other questions like that? Okay. Well, yeah. I remember having a ecology professor at Columbia, and he'd say, "Do you have any questions on across the street at the West End Tavern?" Which was a famous Columbia hangout, which no longer exists. Like so many things in New York, they're not there anymore. Anyway, like so many things everywhere. Okay. Okay. So, as I said, there is a connection between a metric, we know what a metric space is, right? And now we have this idea of topological space. So there is a question given a metric space, what is the associated topological space? If there is a connection, when there is a connection. Now, in the case of the real line, there is the real line is a topological space, and it really arises from the metric space with the metric, with a very familiar metric, in X and Y are in R. This is R1 metric, the real line. We have a metric, right? This metric. Okay. With that metric, we could use this metric. The proper word is induces. This metric kind of induces a topology, and so this is an example. I'll talk more about this in a few minutes about when a metric space induces a topological space. So this metric, in the case of the real, induces a topology. So we'll talk some more about that. Before I do that, though, I want to say some more about open sets, closed sets, and how we can characterize continuity in terms of open sets. So let me define. I haven't really given you the official definition of open set yet, so let me do that first. So let's say that O of a metric space, is open. So this is the word I'm defining. If O is a neighborhood, remember we did define neighborhood. If O is a neighborhood of each of its points. Now remember how we defined neighborhood? Neighborhood contains an open ball, right? So we've got to center it someplace, the radius. Okay. And then from here we could prove the theorem. I'm not going to prove it, but from here this would give us the following theorem: that a subset of a metric space we have a metric space, so we have an underlying set. V is the metric function defined on the space. is an open set. This is a theorem now. Is an open set. We just defined what we mean by open set here. So now we have a theorem. A subset of the metric space is an open set if and only if it can be expressed as the union of open balls. Union of open balls. Okay. This is a theorem that we'll use. Remember an open ball. This is the point A. So this would be an open ball centered at a point A, radius delta. Okay. And it might lie in the neighborhood. Okay. The open ball is the neighborhood of itself, of course, but it can be contained in the neighborhood. So now, so the next thing, here's a theorem, which I'm not going to prove. But here's a theorem which defines continuity in terms of open sets. So we're kind of using open sets now as open sets and as our way of characterizing or defining continuity. So I'll say here's a function that's mapping a metric space. There's a metric space with metric D into another metric space with a metric function, call it D prime. Okay, then F is continuous, so we define continuous function. F is continuous if and only if the logic goes both ways. If for every open set O of Y, the subset F inverse, this is the pre-image, right? The pre-image of O is an open subset of X. Okay, so this is a kind of a topological characterization or description of continuity. Here's a function which maps a metric space to another metric space. We say F is continuous if and only if essentially the pre-image of every open set in Y is an open set or subset of X. Okay? Another definition. Since we've defined open sets, let's define a closed set. A subset S of a metric space is closed. Now defining closed if its complement write it this way, complement is open. Okay. So subset is closed if its complement is open. Here's a little exercise which you can think about. I'm not going to prove it now, but in a metric space, with these definitions of open and closed, see if you can convince yourself that in a metric space, both the empty set and the whole space X are both open and closed. Open and closed. Okay, here's a little exercise for you to think about. So it's not necessarily the case that a set is either open or closed. It could be both. And I think a lot of these basic topological concepts are really handled pretty neatly in these Dover rules. That's why I thought I'd let you know about that. There may be others, but I like those two. Okay, one more. Okay, let's see. Yeah, another definition here. I don't think, did I define isometric metric spaces? I don't think so. Okay, here's the definition. Two metric spaces. Let's say A with its metric, call it B sub A. And B with its metric B sub B. Okay. Two metric spaces are said to be isometric. Define that word isometric if what? There exist inverse functions. F taking A into B, and G taking B into A. Okay, inverse functions, just interchange the name, right? Such that for, let's say, points x, y belonging to the first space A, the distance in that space, the images of x and y is distance measured in this space between x and y, x1 property. Okay, so isometry, if you will. Look at what this is saying. It's saying if I look at the distance between 2 points in A, then that distance is preserved in the image space under the metric refinement of the image space. Okay? But there's a second part. Also for U, V, and V, distance in that metric, G, U, G, V, is distance in this metric of U, V. So, isometry is requires that this distance be preserving goes in both directions. And now there is a theorem that I'll state about isometry. I'm not going to prove it. A necessary and sufficient condition, if and only if that